Hello friends. So today we are going to discuss questions that were asked in the 2000 mains, and total of 12 questions will be discussed. So the first question, and it states that one of the two identical conducting wires of length L is bent in the form of a circular loop and other one into a circular coil of n identical turns. If the same current is passed through both, the ratio of their magnetic field at the center of the loop to the center of the coil, that is BL upon BC, is given as. So here we are having a, you can say, wire that is of length L, and there are two identical wires. One is converted to circular loop and another one is converted to circular loop, coil rather, which is having a n number of identical turns. So this is a major difference between the two. So let us start from here only. We say for a, you can say, the length of the wire is ever L. Therefore, for loop with radius capital R, we can write that our length will be equal to the circumference, that is equal to 2 pi R. So this gives us that our radius will be equal to L upon 2 pi. And for a single loop, we can write this radius, let us suppose R1 will be equal to L upon 2 pi, and its magnetic field at the center for the loop is given as BL, and that will be equal to mu naught I and 2R1. We already know R1, we substitute it here, so we get magnetic field for the single loop will be equal to mu naught I upon 2, and R1 is our L upon 2 pi. So this gives us mu naught L 2L and multiply by 2 pi. Same we can write for the circular coil. For circular coil, we can write our R2 will be equal to L upon 2 pi, and its magnetic field will be equal to that is our B coil and equal to number of turns mu naught I upon twice R2, and this will be also multiplied by number of turns, that is n. We substitute value of R2, we get this as mu naught I upon 2L, and R2 is L upon 2 pi multiplied by N. So this also come as this will be N times R2, N times R2, and this will be giving me R2 is equal to L upon 2 times 2 pi N. Okay, now it's correct one. So this comes as L upon multiply by 2 pi N, and here is also our N. So we can write, or we need a ratio, that is BL upon BC. So we can say that our ratio BL upon BC, this will be equal to BL is our mu naught, this is current I. We have it is mu naught I upon 2L multiplied by 2 pi, and we have this as N mu naught I upon 2L multiplied by 2 pi, and this is multiplied by N. So almost all the terms are going to cancel out. We are left with 1 upon N square. So therefore the ratio of BL upon BC will be 1 upon N square. So option number C is the correct option. Option C is correct. We come to the next question. It was also asked in the 2019 mains, and it states that as shown in figure, two infinitely long identical wires are bent 90 degree and placed in such a way that the segment LP and Q arm are along x-axis, while the segment PS and QN are parallel to y-axis. If OP and OQ are 4 cm and the magnitude of the magnetic field at O is 10 to the power minus 4 Tesla, and the two wires carry equal currents, see figure, the magnitude of the current in each wire and the direction of magnetic field at O will be, take mu naught as 4 pi into 10 to the power minus 7. So this is a given figure. So we have, you can say, two wires. One is from L, P and S, and another one is our M, Q and N. We can divide this two wires into 4 sets. We can call this as LP as first, PS will be our second, QN we can call as a third, and QM we can call it as a fourth. And the net magnetic field, because of these both wires at center O, is given to us. So we can write that the magnetic field due to infinite straight wire at a distance r is given as mu naught I upon 2 pi r. And you can say that magnetic field due to, now these wires are nothing but our semi-infinite wires. Okay, so we can just modify the formula. So we can say magnetic field due to semi-infinite wire you can write this as B semi-infinite is our half of mu naught I multiplied by 2 pi r. So this ultimately comes as mu naught I upon 4 pi r. Now we have total of 4 wires, and if we see closely, the net magnetic field will be the algebraic sum of all these 4 wires. So you can say our magnetic field at the point O, that is our B net, will be equal to magnetic field due to LP plus magnetic field due to PS plus magnetic field due to Qn and magnetic field due to Mn. Now for LP and Mn, we can clearly see, for not Mn but Qn and Qm. So from 2 wires, wire LP and wire Qn, we can see that the point O is going to lie on their extended version. So because of this, the magnetic field due to LP will be 0 and magnetic field due to Qm will be also equal to 0. So magnetic field due to LP will be 0 and due to this Qm will be also equal to 0. So we can say this will be equal to now magnetic field because of the PS and because of the only Qn. And both the wires, the direction of the current is opposite, and because of this, the magnetic field will be in the same direction. Let me draw approximate figure. So we have one wire, current in this direction, point is here, and another wire, the current is in this direction and point is here. So this is the middle point. So if we see using the right hand rule, we can say the magnetic field will be in the same direction for both the cases, and that will be our into the paper. So you can say the magnetic field due to both wires means our PS and Qn is in same direction, which is our into the paper. Therefore they add up. So we can say our net magnetic field B net will be equal to twice into mu naught I upon 4 pi r, and the net magnetic field is given to us, and we can just, this goes by 2, from here we can write our current I will be equal to B net multiply by 2 pi r and divide by mu naught. Now we simply substitute the value. We get our current I will be equal to 10 to the power minus 4 into 2 pi, and this is 4 into 10 to the power minus 2, 4 pi into 10 to the power minus 7. So from here we get that the value of current will be our 20 amperes. And we need to find out the direction, and the direction of the magnetic field at O is into the page, like we said here. So option current is 20 ampere and option number B is the correct option. Option B is correct. Next question. It was also in the 2019 and it states that two very long straight and insulated wires are kept at 90-degree angles from each other in XY plane as shown in the figure. These wires carry currents of equal magnitude I whose direction are shown in the figure. The net magnetic field at a point P will be. So we have two infinite wires and each carrying current I, and we have to find out the net magnetic field at this particular point, that is our P. And we know the general formula for the magnetic field due to a long straight wire is mu naught upon 2 pi r. So here we have two wires. So we can write that magnetic field due to long straight wire at a distance r that is our B, and it is given as mu naught I upon 2 pi r. We have two wires, so we can divide the equation into two parts. Okay, so we can say due to wire 1 magnetic field at P, and the magnetic field at P, let us suppose that is our B1, so this will be coming as mu naught I upon 2 pi, perpendicular distance is D, and direction will be our plus K unit vector. So this is our wire 1 and this is our wire 2. Similarly, we can write for our wire 2, you can say magnetic field due to wire 2 carried our B2 will be mu naught I upon 2 pi d, and the direction in this case will be our minus K unit vector. So because of this wire 2, the magnetic field will be minus k, and due to wire 1 it will be in plus k. So net magnetic field at point P, B is equal to B1 plus B2. Magnitude is same because value of the current as well as distance are same. So we can write this as mu naught I upon 2 pi d, and this comes as plus k unit vector, and this here minus k unit vector, and this gives us magnetic field is equal to 0. So option number A is correct option. Option A is correct. We come to the next question, and it says that the magnitude of magnetic field at the center of an equilateral triangle loop of side 1 meter, which is carrying a current of 10 ampere, is taking mu as 4 pi into 10 to the power minus 7 Newton per meter square. So we are given an equilateral triangle, so we can draw an approximate figure for that. So this is our equilateral triangle, and if we consider that it is having side A and this is the center, so let us join these two vertices, and the perpendicular from this wire, let us suppose that is given as R, and current is flowing in this direction throughout the triangle. And we know now this is a finite wire, so we can write that magnetic field at the center of triangle due to one side, it is given as B, let us call the B side, will be equal to mu naught I upon 4 pi r, and this comes as sine of phi 1 plus sine of phi 2. So this will be angle of phi 1 and the other end will be angle of phi 2. Okay. And this is our equilateral triangle. So this phi 1 and phi 2 will be equal to 60 degree. So you can say phi 1 will be equal to phi 2 is equal to 60 degree. And side is we have taken as A, so we can write for side A, the perpendicular distance from the center to the side of equilateral triangle, perpendicular distance from the center, and center is, let us suppose, our O, center O to side of triangle. Please keep in mind this triangle is our equilateral triangle. So we can write that this distance we called as R will be equal to A 2 square root of 3. Now we can find out the magnetic field, and A is our 1. So we can write this as that R is equal to 1 upon 2 square root of 3. Therefore, magnetic field due to the side will be equal to, we have mu naught I upon 4 pi. R is our 1 upon 2 root 3, and here come as sine of 60 plus sine of 60. Sine 60 is square root of 3 by 2. So we can write this as 4 pi 10 to the power minus 7. Current is given as 10 ampere. So this is 4 pi into 1 upon 2 square root of 3 multiplied by, this will be coming as 2 into 3 divided by 2. And quite simple. So this 4 pi and 4 pi goes away, and this 2 and 2 goes away. So we are left with here as, this will be equal to 10, this will be 10 to the power minus 6, and this will be 2 root 3 multiplied by root 3. Root 3 will be our 3. So this comes as magnetic field due to one side is our 6 into 10 to the power minus 6 Tesla. And we have 3 sides. So the current will be flowing in the same direction. So it will be additive in nature. Therefore, we can say that total magnetic field B, total magnetic field at the center, B will be equal to 3 multiplied by B side. So we get this B will be equal to, this we have 3 into 6, 10 to the power minus 6. This gives us 18 micro Tesla. So the option number D is the correct option. Option D is correct. Next question. And here it states that a thin ring of 10 centimeter radius carries a uniformly distributed charge. The ring rotates at a constant angular speed of 40 pi radian per second about its axis, perpendicular to its plane. If the magnetic field at its center is 3.8 into 10 to the power minus 9 Tesla, then the charge carried by the ring is close to. Take mu naught as 4 pi into 10 to the power minus 7. So in this case, we are given that we have a ring of radius. So let us draw a ring. So this is the center, and let us suppose R is the radius. So this R is the radius, center is O, and it is charge uniformly distributed. So this is a uniform distribution of the charge, and it is rotating with the angular speed of omega. And this charge is, let us suppose, denoted as Q. So we know that the current due to rotating charge is given as Q omega upon 2 pi. Current due to rotating charge is I, which is equal to Q omega divided by 2 pi. And magnetic field at the center of a current carrying loop is given as mu naught I upon 2r. Magnetic field at the center of a current carrying loop at the center, it is given as B, and which will be equal to mu naught I upon 2r. So if you substitute the equation for the current, we can write that our magnetic field B will be equal to, this will be mu naught upon 2r multiplied by q omega and divided by 2 pi, which we can written as mu naught q omega, and we have this is 4 pi r. And we can easily find out the value of charge from here. So we can say that our charge q will be equal to, we can write this as 4 pi r multiplied by magnetic field and divided by mu naught omega. We substitute the values, we get this is 4 pi, radius is our 0.1, magnetic field is given as 3.8 into 10 to the power minus 9, mu naught we already know is our 4 pi into 10 to the power minus 7, and angular frequency is given as to us as 40 pi. So therefore this 4 pi and 4 pi goes away, and we are left with this point. This is our 3.8. Okay. So we can say this will be equal to 0.1, 3.8 into 10 to the power minus 9, and we have here 10 to the power minus 7 into 40 pi. And this, we can say our charge q will be approximately equal to 3.02 into 10 to the power minus 5 coulomb. So this is the charge 3.5 into 10 to the power minus coulomb, and that is closely we can say option number B is the correct one. Option B is correct. Next question. Okay, here it says that find the magnetic field at the point P due to a straight line segment AB of length 6 cm carrying a current of 5 ampere as in figure, taking mu naught as 4 pi into 10 to the power minus 7. So this is a straight conductor carrying a current of 5 ampere, and this is side of 6 ampere. So this is basically isosceles triangle. Okay. And for a finite wire, the amount of magnetic field at point P, we can say will be equal to mu naught I upon 4 pi. If we say this is the perpendicular distance, and let us call this perpendicular distance as A, so that will be divided by 4 pi A into sine of phi 1 plus sine of phi 2. So this angle will be our phi 1, and this angle will be our phi 2. We can say that magnetic field at point P due to a finite wire at a distance A, we can write this as B will be equal to mu naught I upon 4 pi A sine of phi 1 plus sine of phi 2. And this will be our midpoint, and therefore the side will be our 3, both sides. So we can easily find out sine of phi 1 as well as sine of phi 2. So we get this as mu naught is our 4 pi 10 to the power minus 7. Current is given to as 10 ampere, and this is our 4 pi, and we have this as distance d is our, we can find out using by Pythagoras theorem. So this A will be coming equal to as 4. So this will be 4 into 10 to the power minus 2, and we get this as 3 by 5 plus 3 by 5. Current is 10 ampere, 5 ampere, sorry. Current is 5 ampere. So most of the terms here, this 4 pi and 4 pi goes away, and this comes as 6 by 5. Okay. So this 5 also goes away, and this comes as 2. Okay. So this will be our ten to the power minus 7 into, this will be our 6 divided by 4 into 10 to the power minus 2, and this goes by 3 and this goes by 2. Yeah. So we are left with now magnetic field will be our 3 by 2, that is a 1.5 into 10 to the power, this comes as minus of 5 Tesla. And the option is, option number B is the correct one. Option B is correct. Come to the next question, and here it is asked that a particle having the same charge as a electron moves in a circular path of radius 0.5 centimeter under the influence of magnetic field 0.5 Tesla. If the electric field of 100 volt per meter makes it to move in a straight path, then the mass of the particle is. So it means here we are having two fields, one is magnetic and one is electric. So the electric is going to provide it the force, that we can say velocity, and it is also said that it moves in a straight path. Okay. So basically if it is moving in a straight path, then we can say that the forces because of the electric force and magnetic force should be our same. So we are given electric field is given as 100 volt per meter, and the charge is says that is same as of electron. So we say that when charge moves in a straight line in combined electric and magnetic field, combined electric and magnetic field, electric force should be equal to magnetic force. So we can say our Fe should be equal to Fb, or we can write Q multiplied by electric field will be equal to Q, and we have V multiplied by B. And when it is moving in a circular path, so here Q goes with Q, so we are left with that our velocity will be our electric field divided by magnetic field, and it says that it circular path of 0.5 centimeter. If it is moving in a circular path, then the magnetic force provides the centripetal force. Charge moves in a circular path, magnetic force is going to provide the centripetal force. Or we can say our QVB will be equal to mvv square upon r. So we can use these two equations, and here V goes with this, so we are left with that our R will be equal to mv upon qb, and we are supposed to find out mass of the particle. Okay, so let me write this equation again. So from here I can say my mass will be equal to Q BR divided by V. So velocity, we can find out the relationship between the electric and magnetic field. So we can say that our mass will be equal to QB upon R, and this will be over E upon B, which comes as Q B square R upon electric field. And charge is given as of electron, so 1.6 into 10 to the power minus 19. Magnetic field is given to us as 0.5 Tesla, so this is 0.5 whole square, and the radius is given as 0.5 into 10 to the power minus 2, and the electric field is given as of 100, sorry, it is given as 100. So mass will be coming approximately equal to 2 into 10 to the power minus 24 kg. So option number D is the correct option. Option D is correct. So we come to the next question, and it states that in an experiment, electrons are accelerated from rest by applying a voltage of 500 volt. calculate the radius of the path if the magnetic field of 100 millitesla is then applied. In this case, the kinetic energy gained by the electron will be because of the voltage, that is applied voltage. You can say that kinetic energy gained by electron accelerated through a voltage it is given as K is equal to charge multiplied by the voltage, and K is our kinetic energy, so we can say this is equal to half m v square, and we can say magnetic force, as in the presence of magnetic you can say magnetic field, the charge will be moving in the circular path, so the magnetic force is going to provide the necessary centripetal force. So you can say that for circular motion, magnetic force provides the centripetal force. Therefore, we can write that our QVB is equal to mv square r. So we know all the formulas. So first of all, let's calculate use this equation and calculate the kinetic energy. So we know that our K is equal to charge multiplied by the voltage. Charge is 1.62 into 10 to the power minus 19. Voltage is given as 500. So this comes as 8.01 into 10 to the power minus 17. And this is equal to our half m v square. Therefore, we can say that our velocity v will be equal to 2 into 8.01 into 10 to the power minus 17 divided by mass, that is 9.1 into 10 to the power minus 31 and its square root. This comes approximately as 1.32 10 to the power minus 7 meter per second. So we got the velocity, and using this second equation, velocity goes with velocity. From here we can write our radius will be equal to mv divided by qb. So therefore the radius is equal to mv divided by qb. Mass is 9.1 into 10 to the power minus 31. Velocity we just found out is 3.2 into 10 to the power 7. Charge is 1.6, 10 to the power minus 19, and magnetic field is given as millitesla 100 10 to the power minus 3. So this gives us that the radius is approximately equal to 7.54 into 10 to the power minus 4. So it is 7.54 into 10 to the power minus 4. Option number B is correct. B is correct. Next question, and it states that A particle of mass m and charge q is in electric field given by E 2I plus 3j and magnetic field 4j plus 6k. The charged particle is shifted from origin to the point x equal to 1 and y is equal to 1 along a straight line. The magnitude of the total work done is. In this case, we know that the work done by a force is F dot d, where d is the displacement. And here we have both electric field as well as magnetic field. So both will be influencing the force. The total force will be electric force plus magnetic force. But the work done by the magnetic force on the particle, on this charged particle, will always be 0 because of the force is perpendicular to the velocity. So here the work done will be only dependent upon the electric force. So we can say that total work done our total work done W will be equal to work done because of magnetic field plus work done because of the electric field. But work done because of magnetic field is equal to 0. Therefore, we can say that total work done will be equal to work done because of the only electric field. And the formula for the electric field, the work done because of electric field will be equal to force multiplied by our displacement, and the force is our Q multiplied by E and multiplied by D, displacement, and displacement we can easily find out. And it is said that it moves from the origin. So we can say that our D is equal to 1 minus 0 I plus 1 minus 0 J. We need not to write the k unit vector, so this comes as I plus J. And the electric field is given as 2I plus 3j. Therefore, we can write, this is dot product. We can say our work done will be equal to, due to electric field will be, we have our Q and electric field is given as 2I plus 3j and dot I plus j. And this gives us 2 plus 3, this is 5 and comes as 5q. Therefore, total work done, which we have W is equal to WE, and this is equal to 5 times Q. So option number D is the correct option. Option D is correct. So we come to the next question, and in this question it is said that a proton and alpha particle with their masses in the ratio 1:4 and charges ratio 1:2 are accelerated from rest through a potential difference V. If a uniform magnetic field B is set up perpendicular to their velocities, the ratio of the radii, that is radius of proton to radius of alpha, of the circular path described by them will be. So we know that the radius of a circular motion in the magnetic field, that is a standard formula. Radius of circular motion, that is our R, will be equal to mv and this is our Q multiplied by P. Okay. And it is also said that they are accelerated through a potential difference of V. It means the energy, or rather we can say kinetic energy, will be provided by this potential difference. You can say that kinetic energy of particle will be our K, and this will be equal to Q times V, and we can write this as half m v square. So we get our velocity V is equal to 2q v divided by m and its square root. We can use the velocity equation in the radius equation, and this gives us that the radius r will be equal to, we have this as mv, we have m upon qb multiplied by square root of 2qv upon m, and this comes as m upon qb m square, and we are left with, within bracket it will be our 2, sorry, 1 second. Yeah, we can write it as square root of 2mv divided by qb. One second. Q into v, qb, and yeah, this is q square, so this will be our multiply by, sorry, let me correct it again. So we can write this as m and m square, and we have this as q v divided by m, and this comes as q square square root 1 by v, and m goes with m, this q goes with q. Now it's correct equation. So we are left with only square root of let me check, I think, is this correct? I think this looks correct. M upon q multiplied by 1 upon b, and from here we can say our radius is proportional to square root of m upon q. So now we can divide this equation into two parts. We can write that our, for first particle, which is our proton, we can write that our rp is proportional to our mp, and we can write this as qp, and for r alpha we can write this as proportional to m alpha divided by q alpha. So taking the ratio rp upon r alpha, this will be giving us square root of mp upon qp and square root of m alpha upon q alpha. This can be further written as mp upon m alpha, and here we have q alpha upon qp. and we are given that the ratio of their masses is 1:4 and charge is 1:2. So we can write this will be equal to square root of 1 by 4, and this comes as 2 upon 1. So this will be 1 by 2 square root of 2, and we can rationalize it. This will be giving us this cancel out, giving us 1 upon square root of 2. So the ratio of Rp upon R alpha is equal to 1 upon square root of 2. So the option is A is the correct one. Option A is correct. We come to the next question, and it states that an electron moving along x-axis with an initial energy of 100 electron volt enter a region of magnetic field B 1.5 into 10 to the power minus 3 Tesla J unit vector at S. The field extends between x equal to 0 and x equal to 2 centimeter. The electron is detected at point Q on the screen, placed 8 centimeter away from the point S. The distance d between P and Q on the screen is, take electron charge of 1.6 10 to the minus 19 and mass as 9.1 into 10 to the power minus 31 kg. So this is a figure given to us, and it says that it enters the region of magnetic field at S. Okay, so this is the region of magnetic field, and if the magnetic field not present, we can assume that it is going to move in a straight path, but because of the presence of magnetic field, it takes a curved portion and strikes the screen at point Q. So we have to find out what will be this distance Q. So we can redraw this figure in a magnified way and a little bit bigger. And so this is the screen, and it comes from the center point S. So this is our point S, and so this is our magnetic field. So ultimately it is going to follow a curved path. Let us suppose this is the curved path it is being followed, something like this. Let me make this a shorter one. So we have, and we assume that it start moving here, and follow the curved path up till here. Okay. So this is our magnetic field, and this is our final screen. So after that it will be following approximately a straight line. So this distance is, let us suppose, our x, which is our given as 2 centimeter. So this is our 2 centimeter, total distance is x, so this will be our 6 centimeter. And let us suppose this curved path is having the center somewhere here, and if we join it, this will be our radius. So obviously this part will be also our radius r. Okay. And initially it was supposed to move in this direction, so we extend it in this way. So we have to find out this total height, a distance. Okay. And the magnetic field is only within this region that it says that it starts from x equal to 0 to x is equal to 2. So within the magnetic field, it will try to follow a slightly curved path, and after that it will be following a somewhat a straight path. So if we say this angle theta, and this will be giving us this angle will be also equal to theta. So using the trigonometric identity, we can say our sine of theta will be equal to x upon r. Okay. Let us call this point as O, this point as A, this point as B. So we can say in triangle AOB, triangle AOB, this gives us sine of theta will be x upon r. X is our 2 and radius is our radius we need to find out. Radius is not given to us. But in spite of radius, we are given that it is having an initial energy of 100 electron volt. So let me put this R and let me find out the value of R. So we know that the energy of the kinetic energy of the electron, let us suppose that is given as K. Kinetic energy of particle, let us suppose that is given as K, and this K will be equal to half mv square, and this energy will be provided by the 100 electron volt is the initial energy. So we can substitute it later on. And if it is moving in a circular path, so the magnetic force will be providing the necessary centripetal force. Or we can directly write that the radius of circular path is our R. This will be equal to, we can write that QEB will be equal to, QVB will be equal to mb square upon R. Here velocity goes with velocity, and this gives us that the radius R will be equal to mv divided by R QB. So this is our radius, and we can write this into the energy form, and with respect to energy we can say that our radius will be equal to, and this we get this as 2m k square root divided by QB. We substitute value, which is 2 into 9.1 into 10 to the power minus 31 into 100 electron volt, 6 into 10 to the power minus 19 divided and its square root, and we have charge that is 1.6 into 10 to the power minus 19. Magnetic field is given as 1.5 into 10 to the power minus 3. So this gives us that the radius is approximately 2.24 centimeters. Now we can easily find out our sine of theta. So we get sine of theta is our 2 upon 2.24, which is our 0.89. And we can just draw a triangle. So if this is theta, this will be our 0.45, and this will be our 89, and this will be close to our 1. So therefore we can write that our tangent of theta, let us suppose we call this as a height h, and this will be our r minus 1 r 1 minus cos of theta. So we need both these values in order to find out the final solution. So we can say our tangent of theta will be equal to 0.89 divided by 0.54, and this will be equal to h upon 6. So which gives us that our h will be equal to 11.82 centimeters, and this is our total distance d. So d will be equal to h plus r 1 minus cos of theta. So this comes 11.82 plus our radius is 2.24, 1 minus, and this is 0.45. So this gives us value of d is approximately equal to 12.9 centimeters. So this is our option number B is the closest one. So this is the correct option. Option B is correct. So we come to our next question, and it states that a current loop having two circular arcs joined by two radial lines as shown in figure, it carries a current 10 ampere. The magnetic field O at point O will be close to. In this case, we are given that we have a two circular arcs. Okay, so this is our first arc and joined by some, you can see, radial lines, and the current is flowing in this direction, which is given as 10 ampere. We have to find out the magnetic field at this point O, and here the angle is given as 45, that is our pi by 4. So we can say magnetic field due to at the center because of a circular arc. Say that magnetic field at the center of a circular arc, and that is our B is equal to mu naught I upon 4 pi r multiplied by theta, where theta is the angle subtended by the arc in at the center. Theta is the angle subtended by the arc at the center, and we have to find out net magnetic field. So let us consider the arc one by one. Okay. So let us consider first of all the inner arc. For inner arc, we can write our B1 will be equal to mu naught I upon 4 pi r1 multiplied by theta. So we substitute the values and we get this as B1 will be equal to 4 pi into 10 to the power minus 7. Current is given as 10 ampere, and this is our 4 pi, and the inner radius is our 3 centimeter. So this comes as 3 into 10 to the power minus 2 multiplied by pi by 4. So this gives us magnetic field is equal to pi by 12 into 10 to the power minus 4. Similarly, we can write for the outer arc. For outer arc, we can write our B2 will be equal to mu naught I upon 4 pi r2 into theta, and we substitute the value, we get b2 is 4 pi into 10 to the power minus 7, current is given as 10, this is 4 pi, radius will be now 3 plus 3, 3 plus 2, that is 5, 5 into 10 to the power minus 2, and this is pi by 4. And here also this pi, 4 pi cancels out, and this comes as 20. So we can write this will be equal to pi by 20 into 10 to the power minus 4 Tesla. And here the direction of the current in the both arcs is opposite to each other. So because of the inner arc, the magnetic field will be out of the paper, and because of the outer arc it will be into the paper. So B1, that is a magnetic field because of the inner arc, will be out of paper, and B2 will be into the paper. B2, yeah, B2 is outer one, so that will be into the paper. So net magnetic field will be subtraction of the both. So net magnetic field, that's B will be equal to B1 minus B2. So we substitute, we get this as pi by 12, pi we can take as common, pi into 10 to the power minus 4, this comes as 1 upon 12 minus 1 upon 20, and this comes as 5 minus 3 divided by 60. Yeah. So the magnetic field will be approximately equal to 1 into 10 to the power minus 5 Tesla. So the option number 10 to the power minus 5, A is the correct option. Option A is correct. We come to the, okay, it was the last question. So these were the questions that was asked in the year 2000 mains. So total of the 12 questions we solved this time. There are few questions left from the year 2018 mains. We will take during the next time. Thank you.